The purpose of this lab is to go over some of the concepts we hopefully have kind of at least got an idea about from doing the last three labs, the energy conservation with rotation, rubber band, and spring. So the big thing is energy conservation. So the basic idea is all the energy you put into the system always equals all the energy you get out. That's always true everywhere in the universe. All the energy you put in is what you get out. So far, what energies have we talked about? I could do some work on a system that puts energy in a system. I could have some potential energy to start with. I've got something up on a table or at some height. In fact, everything has potential energy to start with. You can even start it at zero, but it always has a potential energy. For example, what's the potential energy of this this yellow eraser? Well, you could say it's zero because it's on the tray. But if I slid it off the tray and it fell, it would speed up. So I could say, well, it's 1 meter from the floor, so it has mgh, where my h is 1 meter and whatever this weighs. Let's say it's 1 newton. Then I'd say it had a potential energy of 10. But what if I drop it out the window? Now I'm dropping it 30 meters instead of 1 meter. So it's totally arbitrary what your starting potential energy is. I could say this is zero. I could say the floor is zero. I could say the top of the board is zero. What's important is whatever I start with, if my height doesn't change, then my potential energy in will equal my potential energy out. So what really happens in all these problems, it's the change in potential energy. So you can have a negative potential energy. If I say this is zero, then if I go below that, my potential energy is negative. So again, let's start back at the beginning. I could have work that I put into a system. I could have potential energy I put into a system. I could have a spring that's stretched. That means I start with a potential energy. I could have a linear kinetic energy, so something's moving. It doesn't have to be speeding up. If it's moving, it has energy. So if it's moving in a straight line, that's linear. If it's spinning, that's rotational. And you can have both at the same time. So everything I put in is going to equal everything I put out, plus if I have some friction, which in real life we always do, there's some heat loss. This will always balance. And if you take this basic idea, that's really all we need to know to solve all the problems on our worksheets. So let's look at how this applies to the labs. So this, So here's my ramp, okay? I'm going to start here with a height, so I have a potential energy. I'm not going to be moving at the beginning. So let's pause this. So it's sitting there, not moving. It has a potential energy. There's no spring, okay? I'm starting the experiment with the ring already here, so there's no work because I'm starting from this position. So it's just sitting there. It's not moving, it's not spinning, so the only energy available is the potential energy. After I let go, it starts sliding down. So however fast it's going, as it goes down, it's dropping, it's losing potential energy. That potential energy you lost, that's my input, right? So my energy in has to equal the energy out. So I'd have no work, that's zero. I have no spring, that's zero. In fact, if I want, I can say my potential energy is zero. I can make all these zero to start with. Then however far I go down, I now have a negative potential energy. So I've lost that. That potential energy I lost had to go somewhere. It goes into two things, my linear potential energy and my rotational. So this equation, we're turning out that if I want to say the floor is zero, then I would take my mass times my g times my height would be what I put in, because all the rest of these don't have a spring. I'm not moving, so those are zero. There's no work involved because I started the experiment with the ring just sitting there. That has to turn into my new potential energy, which is going to be lower. That's going to be smaller because it's going to go down to the floor, so that's going to be zero. So I lose all of this, and that goes into these two potential the kinetic energies plus some heat loss. Now in the word problems, we usually ignore the heat loss. Not always, but usually. So if it's frictionless, we can ignore that. So at the faster it goes faster and it spins. Then I get, as I as I lose more height, I get more kinetic energy. That's how that one works. This was our friend, the disc. We had trouble. The problem with this lab is that the rubber band may or may not exactly follow Hooke's law, but it has some potential energy. So I put it on the rubber band. I have stretched that rubber band. There's potential energy in that rubber band. It's stored. Now, I did some work to pull it back, okay? And that work would equal the energy in the rubber band, but in our problems, we're usually going to ignore that work unless it asks you for that, okay? So if I start from with the rubber band pulled back, the work's already done. So again, what do I have here? I've ignored my work in because I'm starting the lab after that's done. So I have the situation where I'm flat, so that's 0. My spring is like a rubber band, so I've got a certain amount of energy here, okay? I'm not moving, so that's 0. When I let go of the rubber band, all this energy is going to turn into just kinetic energy because I'm not going up or down, so I haven't changed my potential. It's still 0. I'm not spinning, so I haven't done that, and we're going to ignore the heat loss. So I let go of it. So that means for the formulas, right now that rubber band is no longer stretched. So all the energy that was stored in the rubber band has gone into this disk. So my 1/2 K delta X squared that was in the rubber band has turned into 1/2 mv squared. One last problem. This one's the most complicated, which I'm sure makes you happy. So I have an unstretched spring. There's no potential energy in the spring. It's not moving. There's no kinetic energy. And we're going to start, the easy way to work this problem is to say my potential energy right here is 0. So when I let go and it goes down, I'm losing potential energy. As this weight goes down, it's losing potential energy. Where does that go? Well, in reality, some of it goes into the heat loss, but the rest of it goes into 2 parts. Right when you let go, the spring doesn't pull very hard, so most of the energy is going into kinetic energy because it really starts speeding up. It goes faster, faster, faster. Then all of a sudden, the spring gets stretched so much, it starts taking more and more of the energy. It takes it away, both the potential energy, and it starts taking away the kinetic energy. So all of a sudden I get all the way to the bottom. So when I get to the bottom, it's not moving. So all of the potential energy has turned into spring energy. So this one, if I start at the top and I go to the bottom, I can ignore kinetic. If I'm in the middle, I have to take account of that. So that's how those are the concepts that we're going to apply to the worksheets, and I'll have videos on each of the worksheets.